Cool. So last week we were basically talking about loops. So while loop, full loop, and a lot of like nuance about, you know, loops can get kind of tricky sometimes. Hmm. Um, yeah. So the simplest form is like while loop, where you just do, check for this while this is true, then we do this. So that's basically, look at it and you know what it is. Pretty straightforward. Now you have like break, return, exit, and we talk about it. It's a little bit tricky because there's like different scope, and by doing different um command, you will go to different places. So if you do break, it will get out of the most inner loopable block that you are in. So in this case, it's the while loop. So you will break this while loop and go outside of that and then do something else here. But if you do return, it will instead look at the function that you are in. So this case, you are in this function void row. So now return is for function. So break is to sort of like a return for your while for the loop that you are in. And return is to look at the function and get out of the function. So in this case, do something else won't be executed if you are running that return. And exit is even worse, that the whole program will just shut down. So there are multiple ways to stop a loop or things like that to control how the program work. But basically, you just need to get a sense where the block, where is the function, where is the while loop, where is the whole program you're working on. We talk about nested loops. So you can actually go over two while loop at the same time. And in this case, you see that this y equals 0. Last time I was trying this and then I forgot it. And that's why, that's all the problem about while loop. Because oftentimes what you want to do is that, well, you initialize y equals 0. And then you check for, whether y is still smaller than 200. And then you do increment. So this pattern showing up again and again. And that's why people want to, have another loop. And that's why we have for loop. Well, I don't have a for loop slides here. Anyway, so that's what for loop is for. So this is for loop. So you have for loop where you initialize and then you check for the condition and then you do increment or update. You don't necessarily need to be increment. You can also do reverse. You can take one off each time you run it. But basically that's what for loop is for, a more, I don't know, neater way to basically just do while loop with initialization, while loop, and plus update. So you can do regular polygons. Basically, you just increment the alpha value, so the angle, not alpha value. So you just go from angle for depending on how many edges you have, like 2 pi divided by n. So in this case, 2 pi divided by 5. So each time you will go 1/5 the 2 pi. So 2 pi will be the circle, 360 degree basically. But 2 pi will be the way how we do it in processing. So in this case, 2 pi divided by 5, you started from 0 angle and you check whether it's 2 pi and then you just mirror. Then you get regular polygons. And one thing convenient with for loop is that you can also do this modulo operator, where you can just check for, whether it's like, remember is 0, remember is 1, remember is 2, remainder is 2. Then you can do this like alternating colors or alternating whatever. And then we look at this grid of circles. You can still do nested for loop just as you can do nested while loop. But in this case, it's much easier because you won't forget to initialize your index like I did for the while loop. So that's why people like for loop, and that's why for loop exists. And well, we will talk about this, even though we won't get into details, but this is always very cool to look at. So this is something called recursion. So recursion is different from loop, where the recursion is also the way to do loops. And there's also a theorem saying that every recursion function can actually be represented as a loop. And a fun fact is that in NASA, you cannot write recursion, because recursion, there is not guarantee to end. So oftentimes, and you will have a memory stack building up. So NASA have an official role that whatever code base in NASA, you cannot do recursion. But anyway, recursion is fun, especially for generative art. So this is sort of like a example of recursion. And what we are doing here is that think about this row where you have the bigger circle, you put two circles in the last circle. Now zoom into each of these two smaller circles, put two circles in each of these two smaller circles. And now look at the four smallest circle. Now put two circles into each of those. And then you just go over again and again and again. And this is what you get for, infinite case. So this is basically the idea of recursion, that you are just going recursively, just doing the same things again and again, recursively. So it's a little bit different from for loop. For loop is more like, you are not going deeper. You are doing at the same level, that you just repeat doing the same thing again and again. But recursion is that you are doing the same thing, but one step further, deeper into, a different scale. And so that's why recursion is fun. So how do you do recursion? Well, for that, this is all you need. So, that's the beauty of recursion, that you can use this to create that. So what's happening here is that, this is our main function. Forget about this at the moment. This is our main function. What we do is void draw, and then we do circle 200, 200, 400, and we will draw circles 200, 200, W. So first you draw this bigger circle. And now what you want to do is draw inside this. Okay, so I guess we could just get our setting, get processing up. Oh, it's here. Oh, by the way, if you don't like the colors, you can actually change the theme if you like. There's different theme. You're more creative. But for the sake of cleanness, we just keep using the default theme. Anyway, so let's just do this. Let's still do the voice setup thing. Setup. Let's do size 400, 400. Pro. So now what we want to do, we want to get started with a circle that's big enough, 200, 200, 400. Let's diameter, Control R to run. Where is it? Yeah, it's here. So cool. Now we get this big circle. So typically what we want to do is that we want to add two circles to that. Now we want to do 100, 100, 200. No, 100, 100, 200, 100, 200, 200. So this will be 200, 200. This will be, X will be 100, but Y is still the same. So 100, 200. So this is what we want. And now the circle should be smaller. So now you get a circle here. And now you want to get the other circle here. It's 300. And so that's what you want to do. So basically now you want to write a function to do that. Draw circles. Okay, so now for now we just forget about all the recursive part. Let's just assume that we know where we are at. So if I restart the program, oops, I forgot to code this function, draw circles. Okay. Misspell. Spell again. Cool. So this is what you get. So now the idea is that this is what we got. We want this function to depends on the current position. So, you know, look at what we have here. We have like 200, 200, 400. So now we are sort of somewhere starting from the 200 point. So what we want to do is that, well, starting from 200, 200, assuming this is what we will send into the program. So assuming here, we want to send 200, 200, and that's it. So now we will get two input here, float x and float y. Likely I should follow what we have here. 200, 200, and w. So this will be the size of the next case. What am I doing? W is 100. Anyway, forget about it. So this will be, we also want another parameter, which is float w, which will be the size. So let's say we have this. So what we want is that starting from this point, now we want to get to circle here. So we want this function to do this. Given 200, 200, we want to get two circle outside of it, one at the right, one at the left, with the diameter of 200. So you need three parameters. One is that where's the central point, x, y, and now what's the width, the diameter of that shape. So what you will get here? So basically now you got everything. So you will be in the same y, be in the same y, be in the, you know where that are. So another tricky part is how do you determine this 100 and 300? Oh, I have a typo here. So, you know, pretty much this still do the same thing. But now how can we calculate that 100 and 300? So what we can do is that we basically want this point, the x point would be the anchor point 200. And now we minus half of the size of the circle. So now we want to do this 200 minus width divided by 2. So this is what you can do. So you have 200 minus width divided by 2. And now this becomes 200 plus half the width. So this will be 200 plus width divided by 2. So let's see what this, how does this work? Divided by 2. So, you know, you pretty much get the same thing again. But now the tricky part is that now we are done with this. So, you know, you go from this, well, you draw the bigger circle, and then you draw the smaller circle. And now what you want to do is that, well, you want to draw two other circles here, but at the same time, you want to keep doing this again. So now you want to redo this whole thing again. So now what you will be doing, that's the recursion is about. Now you want to call these functions again, call yourself. So notice that these throw circles will call yourself again. Now, what would be the new anchor point? So now you want to draw two smaller circles here in the left-hand side. You want to draw this. So now the first circle will draw the left bigger circle, but now you want to keep calling the same function again to get the smaller blue, where x is 200 minus w divided by 2, the same y, and then our width would be half the size. So this is what you can get for the left-hand side. Was Stack Overflow. So that basically means that it just break. Let me see. If let me add the stopping criteria here. I will get into that later. Um, so- cool. So okay, cool. Now you see, it's just keep getting the left-hand side somehow. And so now we just need to finish the right-hand side. So what we will get is that for the right-hand side, what you want to do is 200 minus W minus 2. Now you want to do plus sign. And this is somehow what you get. So what's going on here? I think I missed something. Um, let me see. This is always a mess for recursion. So you're starting from 200 minus, so the draw circle thing is XY here, and W is 200. Now W become half. And now the new anchor point is 200 minus W minus 2. That should be it. What's going on? So you send 200 and you have 100. Let's show what this is. 200 minus. So you can do print to show at this part what you are printing here. So I will, oh shit. Let me just return. Cool. Oh, it keeps showing stuff. What's going on? So it code the same thing again and again. Did I miss something? That's weird. Let me see. Somehow I divided by 4. Why is that the case? Oh, I think oh, I messed up with something. Okay, cool. Now I see what's the issue. Let me stop it. So W is now, what's the W here? W now is 200, so this is 200. Now we want to move this thing for only 100. So that would be W minus 2. So that would be 100 actually. What did I miss? Anyway, let's try it. Divide it by 4 and see how it goes. Huh. Okay, this is so messed up. Let me see what's the original plan I was doing here. Um, why does this stop? Well, let me grab my original file. Well, that's why recursion is always tricky. Okay, this is the original file that I have. Cool. So originally I'm doing float, W equal 400. That's why we have these here. Oh, I think you need to draw this circle first. And then you draw the rest. Is that the case? Okay, anyway, we'll just go with this. So what we're doing here is that first you will just stop when the width is too small. If you don't do this, the whole program will just crash because it will just keep doing, like 0.1 pixel, 0.01 pixel. It doesn't make any sense. So what you're doing is that, well, you first draw the left-hand side circle, and then you recall yourself again with smaller size. And you always will sort of like mess up with all these numbers. So you got to figure out how you decrease those numbers. Um, but anyway, what you will see is that originally you are calling W. You are drawing the circle with this W is -2, but now the next time you are decreasing that shape at the same time. So that might be the reason. So now, oh, okay. So that's why we shouldn't divide it by 2. Maybe that's the case. Oops. We should divide this by 2 and divide this by 2, divide this by 2, divide this by 2. It will be very small. Okay, so that's why. Originally, you want to do 400. Oops. And now we mess up again. So now these will be divided by 4. Oh, you shouldn't use 2. This should be x. Okay, we're close. I think this should work. No. Anyway, kind of mess up. I think these will be 4. Okay, yeah, that's all the way back to what I have originally. So I guess there's just a lot of details here. So originally you send the 400 thing, so W should be set up as, so this is the original W equal 400. So the first thing you do, the first circle, you are drawing, x minus W divided by 4. So you started from this x, which is 200, 200. So you started with that x minus W minus 4. So you get 300 here. So you basically draw a circle at this point, and you have the diameter as half W, which is 200. So you will get the reciprocal here, and then you do the same thing for this. Now you have, x plus W, quarter W, y, W minus 2, you get W half W, so you get the right reciprocal. So now you want to go inside, zoom it in. So now what you want to do is that now you have a new anchor point. Now your anchor point become this point, which is, W minus X minus W divided by 4. And then you have the same Y. Now your shape, your bigger W becomes half the size. And that's why you code this again. And this will also draw another 2 circle in the right-hand side, and then keep doing this again and again. And that's whole the whole recursion is about. And always shaky to get all the parameters correct. So there's also a way, if you don't like it, to become something like this, dirty, messy line in the middle. So you can actually just break it in a certain level. So what you want to do is just to add the level parameter here, and this level will be decreased each step you go inside the level. So you can think about it. Well, we started from level 6, the outer level. And then whenever you go inside it, it will be L equal 5, L equal 4, L equal 3, L equal 2. And at some point when L is smaller than 1, we are done. So that way you can actually stop this recursion at a certain level. And sometimes it could be nice to do it. So again, we won't go into recursion. Recursion is very fun, but also very chaotic. And you can actually find a lot of very interesting example by using recursion. And there's a theorem basically in computer science theory where any recursive function can be written using the loop. But it can be really messy if you want to translate a recursion function into a loop. Loops are usually faster and use less memory. Recursion function are sometimes easier to write. Anyway, I'll skip this. But basically there are some rule of thumb, but most of the time it's just like there's no way you can use other way to do it. There's just usually one single simple way to do it. So this is another sample about recursive tree. So you can also use recursion to do some kind of these. So this is like a perfectly symmetry one. You can also determine, the relationship between, the right trunk to the left, trunk. And you can also have some angle of difference. So how you draw this is that, well, pretty much you start with this edge. This is the thing that you have. And now look at what's going on for the next part of it is that we go from this edge and we go from this degree and then we turn it slightly at the right and at the left. So clockwise and counterclockwise, but with a shorter length. So for each of this, trunk, you will get two different branches. So one at the right, one at the left. Now keep going. Now you get another branch. Now you are going from this position, but now you go slightly right and left. So in this place, you are going from this way, and then you turn it clockwise and counterclockwise to get these two branches. And you keep doing that. Now you go from this, and then left and right, go from this, left and right, from this, left and right, go from this, left. Right. And you just keep doing that. And that's what you get. And what I'm showing here is that I just use the mouse X to determine the angle. So, the wider it is, now it becomes much easier to become a curvy shape when you get a larger starting angle. And this is the code. As you see, recursion is something that after you write it, you will appreciate its beauty. And while you're working on it, you hate it. So as I just showed that I failed to do it in the first place. But anyway, it's very interesting to look at all these recursion code because it's so beautiful, but at the same time, if you want to write it, you will hate it. So first thing, always you want the stopping criteria, where here what we are doing is that when this tiny branch is too short, so edge shorter than 2, meaning that it's not even 1 pixel. It's just only 1 pixel. If it's just 1 pixel, you add a branch of 1 pixel. What does that mean? We just stop there. So now if you look at the tip, the shortest branch is 2 pixels. Because if it's 1 pixel, then it will break this thing. And the core recursion happens here. So the branch edge is when you start it. Now you want to add 2 branch here. So one at the left, one at the right. And so this will be the right branch. This will be the left branch. And if you look at how they code itself again, now your edge, your height becomes shorter. So you will have the recursion. So you go into this, now you call yourself again, and you code this way again. So it will be exactly twice. And you will enter this branch, it will do twice. So you will just like explode into power law, to this power of whatever level you have. And there's something about push matrix, rotate, translate, things like this, pop matrix. We will go into that when we enter 3D space. You can actually use processing to do 3D. And this is just a different way to do stuff. We can quickly go over that. So matrix transforms is a different way to do it in processing. So let's take a sample. So, the typical way how we do a circle, at least what we've been doing so far, say 200, 200, 200. Oh, forgot to set the canvas size 400, 400. Where is it? Oh, yeah, it's here. So this is a typical way we do it. Um, it's fine, but there's also another way where you can do transform 200. Am I doing the right way? Oh, translate, not transform. Translate 200, 200. And now you do 0, 0, 200. Oh, like this. Translate. So this is another way to do the same thing. So translate will sort of like move your whole grid system rather than drawing stuff there. So so the first example is that we do 200, 200, 200. So that means that, well, at the center of 200, 200, we draw a circle of diameter 200. Now what's going on here is that translate 200, 200. So now what's going on is that, well, this is your original canvas. Now you want to move the origin to 200, 200. So now the new, this will be the new coordinate. Let me get rid of these to see better. So this will be the new coordinate. The origin will be in the middle. And now it goes from to the left and to the bottom. And now if you do circle 0, 0, 200, now 0, 0 become at this point. So this is the way how you can, translate that thing. And you can also do rotation. So you can also do, I guess circle is very tricky to show. What you can do is rotation. Square. So let's see. Void setup. What you get? We will have a float, A equals 0. This is the angle that we are doing our rotation setup. Roll. And we will do this translate once. Okay, so rotate for 0.1. We can get rid of this. Let's see, square. What did I do wrong? Square. Oh, cool. Like we slope. Um, well, it's where you need the float. So you need a float. So what you're seeing here is that you rotate the whole things. Translate should be here. Okay, let's do it this way. So you translate to the center of the translate to the center. So now your grid is at the center, and now you are drawing the circle 0, 0, 200. And now if rotate is 0, oops, left that down. If rotation is 0, it would do nothing. But now see what I do when I do 0.1. Now it will be slightly off. 0.2. It will be more turned. So, the rotation will sort of like redefine your axis. You turn this axis around. So you are still drawing this square 0, 0, 200, but now that your axis become slightly tilted. And so they can actually create a lot of like interesting stuff if you want. So what you can do is that, for example, you can do float angle equals 0 to start with, and then you just keep add in that angle with 0.1. So A plus 0.1. So you rotate, so you translate to the middle, you rotate A, but this A will increase over time. So what you will get is just like a square that's just rotating. And so if you do background 50 so that it won't get that, and we can make it slower, then you can get something like this. So, this is very handy, especially when you're working on something like this. Think about how you do this without all the rotation thing. It will be very tricky because how do you even define where it is? And you have to calculate all these things. So translate and rotation, this matrix transform is very handy, especially when you want to rotate something. So essentially the idea is that, well, we are not rotating this object itself. We are rotating the whole coordinate system. And by turning that coordinate system, but keeping where the square is, you are actually rotating that square. Question on this? We will get into more details on this. This is likely just, whenever you want to rotate, that's where you want to use it in 2D case. But in 3D case, that's the only way we can do stuff. So we will get to that in 3D case. Okay, so what's going on here is that we have this push matrix. So what's going on with this push matrix is that push is that there's a magical matrix stack. Think about it like a garbage bin, maybe not garbage bin, recycle bin. You have a recycle bin. So what you do is that, well, this is your original matrix, which is upright, just the way as it is, like the black one here. This is the original one. Now, okay, now you just push it. So you save it here. Okay, now you do all the shit. So you want to rotate, you change it, and then you translate, you move stuff here. Now you go from here and then you do all the stuff and you do the branch. And after that, now that's reverted back to our original things because you don't want to stay at that weird grid space because you tilt it, you do, random stuff, but now you want to go back to the original one. And that's where you do this pop matrix. So this is why this whole script is very tricky because what we are doing now is that, well, we started from the original grid space, and now we rotate it, we translate it to somewhere else, and we start drawing our stuff, but we want to go back to our original matrix. And the same thing happened for the left branch. You push so that you store here, and then you do whatever you like. At the end, you get it back. Cool. That's all we got for recursion. Again, recursion is very, very, very chaotic. But you can do all the cool things. So this is one example. There's tons of other examples that you can do to get all the what we call fractal. So fractal is cool. So you can do all sort of like different fractal shapes. Some of them is, you can definitely do this if you can figure it out. And these are some of the other famous fractal. This is like you like broccoli kind of. So this is like the fractal that we just showed. So there's a tons of different things. So if you do the left and right differently, so look at this, like the right angle and the left angle is different and different lengths, you can do the different curvy shape. And there's a bunch of other fractal things. So all of these, you can actually just use the same idea to do that. But for other things, these could be very tricky to get it up. These could be complex. Cool. Yeah, again, we won't go into much detail about recursion. It's a whole lot of interesting stuff, but it's also a whole lot of mess. But some of the most coolest art I've seen is generated by recursion. Cool. So today we will talk about data types and arrays. We will get into this, even though it's not technically about arrays, it's just more on colors. But anyway, that's where we head into. Cool. Any questions so far? Likely simple enough. Things will get real tricky in next week, not today, when we go into object. Cool. So this is, I think I got the wrong one. This is fall 2024. So yeah, so far we are still a step from getting closer to object. That will be the most tricky part of the whole processing part. But still we have one step to that. So we will talk about all the different data types. We sort of like just use them without understanding what those are. You know, float is like, yeah, we just use it. And integer, fair enough. I mean, it's obvious enough. But we will dig a little bit into data types and talk about arrays. And then next week we will talk about objects. That's the big boss of this. So data types. So this is the hierarchy of data types. So primitive, meaning that it's something naturally on your machine. Your machine has to support that. And non-primitive, meaning that it's something where you created or created some built-in thing that's unnatural for the computer. So primitive is mostly all the thing we talk about, like Boolean, just like 1 or 0, true or false, whatever, yes or no, things like that. Binary, 2 options. Numeric, a lot of different things, integer, floating points. So we mainly just use this int and float thing, but it's actually much more than that. Integer, you have like different precision. So byte is the simplest one. We talk about like in colors where you have like that, hex code where you have, FF, well, RGB FF000. This will be the red color that we have. So R will be FF, G will be 00, 00 will be. So this will be 256. So 256 is roughly basically just what byte can represent. So each of these is represented by 1 byte. And so 1 byte is the minimum sort of like currency on your machine. Whenever you're running this Java script, you're running Chrome, you're running PowerPoint. Whenever your program wants to communicate with your machine, it has to ask for something. And byte is the currency. I want to ask for a memory to store something that I have. I will ask for 1 byte. And for sure, it's like now actually 256 doesn't fit my need any larger than that. Then I do the short. An integer is much larger than that. We need 4 bytes for integer or 8 bytes for long. So byte is the currency, like what's the minimum size, the memory that you can request. And the same for float and double. So basically there are different precisions. There's also character, but character is basically just representing as a number internally. It's integer, I believe. We'll see later. And there is also non-primitive. One of the things that you've already encountered is string. So string is where you see it in homework 1. We just use it as this without knowing what the heck is going on in string. But we will see it next week. Array, we will see you later today. And then this is the tricky one, user-defined class. And class object is what the biggest part of the object-oriented programming. And processing is based on Java, so it's also object-oriented. Cool, we'll get into that next week. And these two are supported in Java, but it doesn't actually are well supported in processing. Most of the function in processing will just convert long to int and double to float. So, most of the time, int and float is good enough. So as I said, Boolean, no, not Boolean, like byte is the minimum amount that you can do. So for Boolean, you actually just need 1 bit, but byte will give you 8 bits of that. So a byte is basically well, we're getting into some computer architecture thing, but good to know what's going on. So by this, well, we have basically 8 slots to store your information. So what you can do with this 8 slot, for each slot, you can only do 0 or 1. So the next number you can represent is 0, 0, 0, 0, 0, 0, 0, 1. And all the way to 1, 1, 1, 1, 1. 1. So this is the maximum different values you can represent in this thing. But unfortunately, byte is the minimum things we can do. So even with the Boolean, it will take up 1 byte. So this will be a more accurate way to do it. So, from negative 128, so this will be negative 128, this will be negative 127, and all the way to this 127. And so 0 will be somewhere here, likely 0, 1, 1, 1, 1, 1, 1, 1, 1. Somewhere here, it will be 0. Not quite sure, but somewhere here. Or, yeah. Or ones, I think it's 1, 0, 0, 0. So 1, 0, 0, 0, 0, 0, 0, 0. This will be 0. Anyway, so that's the whole chunk of like 256 possibility of all these different numbers that you can represent, and you will use the full byte. And now, things get trickier. Now you have integer, you have long, now you have more chunks, so you can represent a larger number, basically. And float and double, these are the range. It's very tricky because it's in floating numbers, so who knows what those means, but float is good enough. I guess that's all you need to know. And usually we refer to int and float, single precision. Sometimes you will see that, double precision for long and double, but we won't look into that. For color, as I said, in byte for 4 is likely. Oh yeah, that's true. So as I said, RGB is, so color is actually RGB, and there's one extra point that's alpha value. We will talk about it later for transparency. So basically you need 4 of these numbers. And as I said, RGB go from 0 all the way to 255. So you need a byte to store each channel. So you will need a byte for R, 1 channel for 1 byte for G, 1 byte for B, 1 byte for A, alpha value, the transparency. So you need 4 bytes. So if everything is 0, it will default to a black color. Cool, and character, we will get into that later. But basically that's also another way using numbers to represent character. Cool, and so for all character is like something you did in homework 1. Like those are text, 0, A, B, C, D, or new line, exclamation mark, comma, semicolon, whatever. Cool. So a little bit more on floating number, just to give you a sense what's going on in floating number. So what we will do is that we have 32 of these numbers. So as I said, whenever you request something in the computer, you will get a bunch of numbers, and that's the numbers that you can represent. So you will get 32 positions, and each of them could be either 0 or 1. So for floating number, the first thing is the sign. So you will get either it's positive or negative. So if it's positive, it's 0, is it? And 1 is negative, or the opposite. Exponent is where you get the sort of like how you represent it. And mantissa, I don't know how to pronounce it, mantissa. Whatever, you have 23 bits for that. That will be the actual numbers that you have. So think about this way. It will be sign times mantissa times 2 to the power of exponent. So that's why, floating number is very tricky, because it's in base 2. So nobody really knows, if you look at these numbers, how you can interpret that. Because you have to turn this exponent into some base 2 stuff, and then you do the all the other numbers. But basically these things would be, you're basically, think about 3.14159, that's, pi. Then you want to store 314159 in one part. That's the mantissa. And then you want to determine where the point is by the exponent. But that's the base 10 case. Now you are doing base 2. So things will be a little bit tricky. But anyway, that's how the floating number is represented. And you get a sense that, well, not something easily interpretable. And double is where you get more beats. But to be honest, most of the time you don't need those. You can have way too much, too many beats for that. Cool. Well, this is more relevant if you want to do data type conversion, but it's very straightforward. You just call it and then you just change it. So if X is like integer, if you want to turn it into Boolean, just Boolean that X. So by doing data type conversion, you have to sort of worry about the hierarchy of data types. So as I said, there is like the longer, so by short int long, this will be all the integer, but they will be larger, getting larger at each step. So of course, if you have more space to store the same amount of information, you should pretty much get a lossless conversion. So from byte to short, of course, short will absorb everything you can represent it by, but provide more stuff, more numbers you can represent. And the same when you go from short to int long, and the same for float to double. So from long to float or integer to float, it's actually not always lossless. It's a little bit tricky, kind of hard to explain, but it can be loosey because of the way how we represent the floating number. So there are some numbers that just too many, trailing numbers that will be discarded when you turn it into a float. But likely you won't get into that. And it's close enough most of the time. So potentially loosey. So everything else would be lossy, potentially. But don't expect lossless conversion. And Boolean could also change it to byte. And character will be somewhere there. Anyway, so floating point to integer conversion. So it behaves like rounding, but not exactly. So if you do integer 1.2, it will be 1. Integer 1.8, it will be 1. So basically round down. But it's also not essentially like that. So if you do minus 1.2, it will be minus 1, minus 1.2, minus 1. So it will be rounding down at the positive part and round up at the negative part. So, to be honest, just don't do this unless you know what you're doing. So a better way to do it is to use round. So this is in Java, it's math.round, but process you can just call round. So if you have round, it's much easier. It's just like the typical way we do rounded. Round 1.2, 1, 1.8, now round up to 2. And the same for negative part. One thing you want to make sure is that round up when in the middle. So 1.5 will be 2, that's obvious, but minus 1.5, you will round up. So you will go to minus 1 instead of minus 2. Cool. So this is what I meant by loosey conversion. When you turn that into the float, you can actually see it. When you try this in processing. So what happened here is that, that's what I just talked about, the lossy conversion, where, you have exponent, you have mantissa. So you want to represent these things in mantissa, but it doesn't have that precision to get all the final trailing numbers. And that's why you potentially get a lossy conversion. Cool. Anyway, this is another way to do data type conversion. You can also do float b equal, like a weird syntax, parentheses float and then a. You will also do that. There's a bunch of more details, but I guess I would just quickly go over that. This is what we call implicit type conversion at the left. So this is something prohibited. So you have an integer a equal 1, and then you do float b equal a, because integer is smaller than float. everything that's in the integer should be able to be represented as a float. So you can do this. But now if you want to turn a float into integer, it's prohibited because the model the machine doesn't know how to turn this 1.5 into integer. So you have to specifically use a or integer a. You have to turn it. You have to convert it explicitly. So I guess these are more important. Integer to Boolean conversion. Everything that's only 0 will go to false. Everything else will be true. This is different in every language. So in Python, it's a 1 will be true. Oh yeah, Python is the same. Everything will be true. Just 0 will be false. So Boolean 1 will be true. Boolean 0 will be false. And Boolean 10 will be true. So everything will be true. So even for negative values, it will be true. Boolean 1.1 doesn't work because it's a float. So for string to Boolean conversion, so you will see that true, 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 whatever true will be true. You can use capital or upper space, lowercase. It's case insensitive. So everything about true will be true, but everything else will be false. So true will be true, false will be false. But if you do like Boolean y, yes, it's still false. So that's something you need to look at. So Boolean 1 is also false, but if you do something, but if you do, this is a very hard to find bug. So sometimes you do Boolean and then you do integer this thing. Now it becomes true. So sometimes you get you get something from the user. So user typing something and you get 1, and then you forgot that your 1 is a character and you just turn it into Boolean and you get a false. So if you want to turn it into the correct Boolean, either you use an if else or you turn it into integer first. That's one very hard to detect bug. Cool. We will talk on colors and we will see that demo that we just saw. Cool. So color is actually also a data type. So color itself, this thing, is a data type. When you type color in processing, it will show up with a different color. So we talk about so many different ways to represent a color. So the simplest way, fill with grayscale, 0 to 255. So 0 will be black, 255 will be white, somewhere in between 127 will be gray. RGB, RGBA, we will talk about A later. And you can also do HSV, hue, saturation, brightness. That's we will get the rainbow effect. You can also do color C to this specific format, like a parenthesis 0, 39, 76. Then you will create a color data type, and now you can also send that into the fill function. So transparency is something very interesting in processing, especially in rendering. Basically, you will have the fourth channel of RGBA or HSVA. So it's fun to blend colors. And so that's what we will be doing. And also, you have the hue, saturation, brightness thing useful for creating rainbow effects. Cool. So that's what we are doing now. Quick exercise and challenge yourself to draw the G clef. It's a funny thing in musicology where people just look at so many different G clef for famous composers. Some of them are very fun. Cool. This shouldn't be too tricky. What you need is the alpha value for transparency. So you can get the transparent effect. Cool. And you want to use mouse X and mouse Y to get the where the circle is. And so you want to use color mode HSV. So what's going on here is that the mouse Y would determine the hue of the color. Something here. Almost done. There's a stroke.
What's the name to get rid of the edges of the circle?
No stroke. Capital S. No stroke. And so one thing interesting about this alpha value is that, well, if you stay here for longer time, that transparency will add up together and now it becomes a solid color. And then you can sort of like see how it blends to another colors. Not quite, but I mean, when the color changes. And if you stay here, it will become a solid color because that alpha value will just add up over the time. Good? Anything close?
Yeah. But for the smooth transitions between the color, is it just a
Smooth transition. So what I'm doing is that mouse Y will determine the hue.
oh,
Yeah. And you can also turn it into mouse X. Then, now it become, horizontally the rainbow. So everything in the same, y-axis, x-axis would be the same color. That's how I do it. You can set up a different rule. You can also say how far away you are from the circle. So this is more like there's the scratch rainbow painting thing where you just use like a knife or pen to scratch out like a rainbow color underneath it. So that's what we are doing here. We are sort of like, well, this is a rainbow color things, and we are just revealing part of that behind this. We are doing some scratching kind of.
what are the smooth values again on the hue saturation?
Same, 255. Yeah. So everything about color is 255 kind of. Yeah. Cool. So hue, you just want to map 0. So map this is 0, this is height. So you want to go from 0 to high and you want to map it to 0 to 55. So one thing that's very handy is the map function. So you can do map x let me just do this like mouse x, and then there will be 4 numbers after mouse x. It will be 0, height, 0 to 55. So this will sort of like look at 0. This will be 0 to high. And now look at where your mouse x is. Translate that to another scale that's going from 0 to 55 and try to see what that particular number will be. This will return that particular number at the same relative position of that. So that's the map function. It's pretty handy. So now you want to, map 0 to height, where your mouse axis is like 1 1/3 toward the other side. So 0 to 55, what this number will be, somewhere around 200-ish. And map function will give it out. So that's how you can get the hue. Cool. Time to reveal. Cool. We can take a look. So it's what I have. Cool. So what's going on? First, of course, we need to turn it into a color mode, HSV. So now we have hue, saturation, and brightness. We don't want the stroke. Get rid of the stroke. So now this is the tricky part. So you want to determine what the hue is. So again, what we are trying to do here, mouse Y. So you want to turn mouse Y from the scale between 0 and height, where your mouse Y will sit somewhere between this. Now you want to turn the scale to 0 to 55. So 0 to height. So now in this case, 0 to 400, we have mouse X at, say, I don't know, 200-ish. Then what would that number be in 0 to 255? So that's how you get the hue. So now this hue will be in between 0 and 255. That's how you map to a different scale, linear. So now you have the hue. So now you grab the hue, etch the HSV. So now fill, because you set the color mode to HSV. So now this is edge, this is saturation, this is brightness. Saturation, if you get rid of saturation, you won't see the color. So saturation, let's just maximize it. Brightness, again, just maximize it because we have transparencies to control that. So now I set a transparency to 50. And now finally now we set no stroke. We set the fill, we set the color. Now we can just get the circle out. So mouse X, mouse Y, 20. So let's see how it goes. So this is, what you get. So if you look at the single circle that you draw, it will be sort of like transparent. So it's not that full color. But once you stop at this position, what's going on is that, the model is drawing one circle on top of it. So, that transparency will quickly saturate. And now it becomes a solid color with, 0 transparency. So you can change this transparency thing. So if it's 10, then it becomes much fainter. If it's 5, you can barely see it unless you just stop there for a pretty long while, then, it's fine. And if it's too large, you don't really get the transparency effect. Questions? Good. So, transparency could be fun, and messy sometimes when you want to blend colors, but, some of the coolest effect could be done with transparency. Cool. That's what we have. Here I'm just doing a, different way. Mouse divided by flow with X times 255. This is essentially what map is doing. So map function could be very handy. Cool. And this is likely something you've done in homework 1. So we would just quickly go over it and jump to something interesting. Text rendering, the technical part of it is that each single number in character, there's, put it another way, each character can be represented as a number on your machine. So machine doesn't really know what character it is, like what's A, what's B, I don't care. I know numbers, but there's a dictionary that you can know what A is correspond to. So capital A will be 41, lowercase a will be 61. And this is actually not defined by processing. This is defined by, UTF, A UTF, it's 16. So that's how the whole internet is doing it. default encoding is UTF-16, and this is the whole UTF-16 if we plot everything here. So it basically covers not just the letters. There are special codes, but they are also, English. I mean, English, of course, German, French, Japanese, Chinese, Korean characters, lots of characters in UTF-16. So it's just a dictionary where, well, pretty much you have the numbers. And now you look at this dictionary to determine what those characters will be. And that's how, Wikipedia can have so many different, characters in different languages. And that's UTF-16. Their goal is actually trying to cover all the characters, but, at some point it might blow up. Cool. So you can do something like this, even though who knows why we want to do it. Maybe in the exercise, even though that exercise is not that meaningful. But character, you can turn it into capital A. Character 65 will get that character. Integer, if you turn this thing, if you insist, you can actually turn it into integer. Sometimes it can be useful. Most of the time, not quite. But you can do all sort of this. So you can see that, different essence you get. Still find it somewhere in the character dictionary. But, for other character, it will be much trickier. So you can do this. So for this exercise, we are trying to see the two iconic way to do for loop. So working with character is just for fun. Let's just quickly go over it, I guess. So what we can do here is that we want to print the character wall where we have just show the first several characters. So what we can do is that, well, now we need to for loop integer I. So we will go for the X. So I will be the X, Y will be the J. So integer I equals 0, I smaller than 12. In this case, we have 12 number each row, I plus plus. So this will just loop over I from 0, 1, 2, 3, 4, all the way to 11. And that gives you 12 number because you include 0. Okay, so now you have another for loop for the y-axis, j equals 0. So the convention of for loop is that you use I stand for index, and j just stand for the next letter for I. So ijk is usually how we do for loop. So now you have another for loop that's doing I and j. So now what you want to do is that I will go from j0, I0, j0, I1, j0, I2, all the way. So these are all j0, j1, I1, j2, I2, blah, blah, blah. So what you want to do is to see, well, what does that character represent? So you want to get which character you are at. So what you will do is that, for this point, what you want to do is that now you are at the second row. So you want to times j by 12. And then you plus I. So what this will do in the first row, j is 0. So first row, I will be just the first things. And in the first row, j equal 1. The second row, j equal 1. Now it will times 1. So this will be 12, 13, 14, 15, all the way to 23. And this will be 24, 25, 26. So 24 because, j2, I0. So 2 times 12, 24 plus 0. So this is how you get a character. And what you want to do is just to show it, text. Well. Let's just print it first to see what we get. Cool. So you get a lot of like random alien code. But now what you want to do is to show it. So what we can do is that we can do character. Where we have the code. So we can turn this character into the character that we want to show, which is 12 times j plus I. Oops. And now we want to show it somewhere. And so this is pretty much similar to homework 1, where you just show it somewhere. And this somewhere can be a little bit tricky because you want it to be, let's just do, I don't know, 200, 200 and see how it goes. 200, 200 code, and likely it will blow up. Okay, so everything will be there. It's like very ugly. So what we want to do is to move it somewhere else. Oh, text is like the code would be in the front. Whoops. Cool. So everything is showing at this position. That's why it look kind of ugly. So what we want to do is now we want to put everything in different space. So what we can do is that we just use the I and J. So we have the I and J. So we divided these things by 20-ish. So we can do I times 20, J times 20. That should give us something like that. Okay, so now you see where they are. And we want to set the color. I forgot whether we should use fill or let's try this first. It's a fill or stroke. Oh, okay, fill. So now we space them out. So for each of these texts, the position will be I times 20, J times 20. So they will be in their specific spot. And if you increase this number, then you can make it even sparser. Cool. So this is kind of close enough to what we have here. You have to make sure the font size and also what's the the spacing for that. But pretty much this is what you can do. So what you will do is that integer I equals 0, I smaller than 12, I plus plus, to loop over the x-axis and you loop over the y-axis. And how you get the code will be I plus 12 times j, so that you go from 0 to 11, 12 to 23, 24, 25, 26, all the way to the last one would be, 132, 143. Yes. Yeah, 132 to 143. And then you show the text where you know what exactly character you are doing, and this is the XY position. You can compute from just timing I and J by 50. Cool. So there's actually a way you can use one for loop. I would just spell it. We don't have time. But this is the way you can do it. We will go over it next time. So that's where you see the modulo again, where you can just loop over the code from 0 to 144, but now you get the IJ back. And you can get the exactly same thing. Cool. And that's what you have played with in homework 1, but just that you are playing with more characters. Cool. Yeah.